Hey guys, I miss chatting with you, so I hope everything is going well and you're having a great week. This last part of the semester, we're going to move into talking about the atmosphere. So, if we're thinking about Earth's four spheres, we have talked a lot about the geosphere. So, early in the semester, we talk about the geosphere. The last couple of weeks, we've been talking about the hydrosphere, right? So all of our water on Earth. We don't talk a lot about the biosphere in this class, right? You usually talk about the biosphere in biology class, but it has kind of been sprinkled throughout the semester. And now we're going to talk about the atmosphere for these next couple of weeks. And so we're going to talk about kind of that final sphere we haven't covered yet. So when we're thinking about the atmosphere, we first have to think about weather and climate and the difference between the two. And so weather is the state of an atmosphere at a given time and place. So for example, the weather today in North Dakota is pretty crappy. We're having a blizzard. And even though all the snow just melted, now we have more, right? So today's weather is that it's 30 degrees and snowing and sleeting. Yesterday it was beautiful and the sun was out and it was 50 degrees, and that was yesterday's weather. So right now at this moment in time, that's the state of the atmosphere. Climate, on the other hand, is a description of aggregate weather conditions. So it's a description of sort of the average of weather over time. And really the definition, sort of when we switch from talking about weather to climate, is about 30 years of observations. So think of weather as things on the very short term, right? You watch the weather forecast for the next 10 days. There's the Farmer's Almanac that kind of tells you what to expect this year. People are probably talking about how what we expect summer conditions to be like, maybe what we expect flooding to be like this spring. And so those are all things that we would consider weather conversations. Climate is more long-term based talk. So think of things based on averages of lots of years of observations. Could be thinking about sort of the normal conditions. And so when we're thinking about climate data, that can't be used to predict the weather. That's one reason why weather predictions can be a challenge, because we can't use our sort of average climate conditions to make really precise predictions about weather. So both weather and climate are driven by the sun's energy, right? So solar radiation is really important for a lot of processes on Earth, right? We just talked about solar radiation last week when we were thinking about wind moving around, when we were thinking about ocean currents moving around. Those are also driven by solar radiation. And all of the weather systems and those average conditions of climate are based on solar radiation. So weather and climate are both expressed in terms of really basic elements. So those basic elements are air temperature, humidity, cloudiness, precipitation, air pressure, wind speed and direction. So those are the basic elements that we use as scientists to express or characterize weather and climate. So we can talk about, okay, the wind speed today is going to be this, the air pressure is this, we have a 30% chance of precipitation, right? The temperature is going to be a high of this and a low of this. So those are all conditions or expressions that you're probably familiar with just from watching the weather forecast. And so we use basic elements to talk about weather and climate by choosing things that can be measured regularly. So those basic elements that have been selected to talk about weather and climate are things that can be measured regularly, so maybe once a day, and things that can be measured quite easily. So when I was an undergrad in school, I actually worked in a climate lab. So at our university, we had a national weather station, um, basically monitoring site where we went out and recorded every day the high and low temperature, the amount of precipitation, the wind speed and direction, and air pressure, and then that went into the National Weather Service's um, weather and climate database. So these basic elements can be measured quite easily and regularly with lots of stations across the US and across the world. So let's take a step back to the very beginning of the semester, see things are coming full circle, and think about the composition of the atmosphere. So when we talk about air, when we talk about the atmosphere, the scientific definition of air is just the mixture of gases and particles that are composing or making up the atmosphere. And remember that nitrogen is the most abundant gas in the atmosphere. It makes up about 78% of our modern atmosphere. Oxygen is the second most abundant gas. It makes up about 21% of the Earth's atmosphere. And then everything else, all the other gases, make up the remaining 1%. And some important ones that people generally talk about are carbon dioxide and argon, because those are kind of the next two biggest percentages. So some of those smaller things that are important for the atmosphere. Carbon dioxide, even though it only makes up a really small percentage of the amount of gas in the atmosphere, it is a very efficient absorber of energy that is being emitted by the Earth or refracted or bouncing off of the Earth. And it is created or added into our atmosphere, one, through natural processes. We've always had a natural amount of carbon dioxide in the atmosphere, but that amount of carbon dioxide has been accelerated by the burning of fossil fuels, including coal and oil. Water vapor, we've talked a lot about water vapor during the semester. Just remember that this is the gaseous phase of water, and it becomes really important when we're thinking about the atmosphere because the water vapor is also helping to absorb energy, and it is also creating precipitation, creating clouds. And so we'll be talking a lot about water vapor when we talk about precipitation and clouds next week. And then aerosols are also really important in the atmosphere. Remember that aerosols are just really small particles. They can be solids or liquids. So think of like dust and pollen and ash, really, really small microscopic things. They can be either natural or human-made. They're really important to how the atmosphere functions because these are little particles on which water droplets can condense. And we also care a lot about aerosols when we're thinking about atmospheric pollution because they can remain in the atmosphere for a long time because they're so small, they don't easily settle out of the air once they are up in the atmosphere. Another important aspect or element within the atmosphere is ozone. So ozone is 3 oxygen molecules bonded together. And we have ozone largely concentrated about 10 to 50 kilometers above Earth. And in that layer or concentrated part of ozone, 10 to 50 kilometers above Earth, we call that the ozone layer. And the ozone layer is actually really important for how life functions on Earth because it actually is able to absorb UV radiation from the sun. So remember that UV is the harmful radiation from the sun that causes sunburns and suntans and skin cancer. And so the ozone layer is really important because it creates this protective um, layer within the atmosphere that absorbs a lot of UV radiation. And if we didn't have the ozone layer, Earth would not be habitable in the way that we think of life living, right? There are some organisms that can live in really high UV radiation and they would be just fine, but the way that life has evolved on Earth, we would not be able to live without the ozone layer unless we engineered some way to go outside with really high UV. So UV radiation is actually absorbed in the ozone layer because conditions are really perfect where the UV rays can break down that oxygen into that oxygen, 3 oxygens bonded together into separate oxygen molecules. So it's actually a chemical reaction that is occurring within the ozone layer to absorb UV radiation. So you guys have probably heard about the ozone hole or ozone depletion. And this is related to the addition of chemicals into the atmosphere. Largely something called chlorofluorocarbons or CFCs. These are commonly used in refrigeration and aerosol sprays and were particularly heavily used during the last century, sort of during the 60s onward. And they sort of worked to break down the ozone, and so the ozone was depleted by these CFCs. And the Montreal Protocol, which was in 1987, was actually a treaty to phase out the use of CFCs, which has largely worked, and we don't actually use CFCs in our aerosol cans, so not in our hairsprays or in our refrigeration systems anymore. But CFCs are an aerosol that's able to stay in the atmosphere for a really long time. So the ozone, we expect, will return to its pre-1980 levels by 2060 or 2075. So it's going to take a really long time for that damage that we did in the late 1900s to be remedied by the Montreal Protocol. So take a break for me talking to you and answer the following questions. What is the difference between weather and climate? Which 2 gases dominate Earth's modern atmosphere? And what is the Montreal Protocol? The second part of this lecture is talking about the structure of the atmosphere. So the first thing to note is that the atmosphere doesn't actually have an upper boundary. We don't define an upper boundary for the atmosphere. It gets thinner and thinner as you move up in elevation, as you move away from the Earth's surface, and eventually sort of just fades into space. And atmospheric pressure is just the weight of air that's on top of you. So the closer you are to sea level, the more atmospheric pressure there's going to be. So atmospheric pressure is higher when you are close to sea level, and as you go up in elevation, right? So if you go up to the mountains, atmospheric pressure is lower. So this is why people get elevation sickness. It's related to the fact that there's less air, right? The molecules are farther apart. There isn't as much pressure on top of you, and if you are not used to that, you will probably have a hard time breathing and get a little sick if you're not able to acclimate very quickly. So as I said, atmospheric pressure decreases with elevation, and 50% of all of the air in the atmosphere is below 3.5 miles above sea level. So 50% of all the air in the atmosphere is within the 3.5 mile layer surrounding Earth. So as I mentioned, air gets thinner and thinner as you go up in elevation. And so, for example, if you've ever seen the movie Everest, or if you've ever read about people climbing Mount Everest, they use oxygen when they climb really high mountains because there's not enough air even at the top of the tall mountains on Earth's surface for people to breathe very well. The highest place anyone has ever been in the atmosphere is, without being in a space ship, is this man named Felix Baumgartner, who in 2012 went up to 128,000 feet and then jumped out. And so that's called a halo jump. So the record for a halo jump, which is sort of a free fall to Earth's surface, is 128,000 feet up into the atmosphere. So this is the cool thing about the structure of the atmosphere, is that, okay, air gets thinner as we go up in the atmosphere, but temperature also changes with elevation. And so we're able to divide the atmosphere into 4 different layers based on temperature. And there's actually kind of a 5th layer that in the video that's embedded in this PowerPoint, there's an outer layer, but as climatologists, we don't really talk much about it, so we're just going to talk about the 4 main layers based on temperature, which are the troposphere, the stratosphere, the mesosphere, and the thermosphere. The next layer of the atmosphere is the stratosphere. You might have heard this word because there's that saying, your head's up in the stratosphere. So at the bottom of the stratosphere, temperature is actually fairly constant. So see how it's kind of a straight up and down line. And then it gradually begins to increase up to the top of the stratosphere. And you can see that that temperature actually starts to increase because the ozone layer is within the stratosphere. So the important thing to know about the stratosphere is that the ozone layer is within it. And remember that our ozone layer is absorbing UV radiation. And then the top of the stratosphere is called the stratopause. And the final layer of the atmosphere based on temperature is the thermosphere. And so this is our uppermost layer, and temperature is actually increasing towards the top of the thermosphere. So it's coldest at the bottom of the thermosphere and increases as we move upwards. But temperature within the thermosphere is a little different than what we generally think of as temperature on the Earth's surface. So temperature in the definition of the word for everything is actually defined as how fast molecules are moving, But since the molecules that high up in the atmosphere are very sparse, and there's not a lot of them, even though they're moving very fast, they're not running into each other very often. And so they don't generate a lot of heat, even though they're moving very quickly. The cool, really important thing to know about the thermosphere is this is where the aurora borealis is created. I'm really excited now that I live in North Dakota to have a chance to see the aurora. So I'll keep you updated this spring if we see any. So the first thing that we need to think about today when we're thinking about the atmosphere is the idea of atmospheric heat transfer. So as we've been talking about when we talked about the ocean, remember that the sun is the ultimate source of heat, right? So all of the heat, all of the thermal energy on Earth is the result of the sun's solar rays bringing energy to Earth, which is then transformed into heat. So the sun's thermal energy is transferred through the atmosphere and Earth's surface through a variety of ways. And those three main ways that the sun's thermal energy is transferred through the Earth's atmosphere and surface are conduction, convection, and radiation. So conduction is the process of heat transfer through a matter. And so this has to do with the fact that heat likes to flow from high temperature to low temperature. So heat likes to flow along a gradient from high to low, just like winds blow from a high to low pressure gradient. And conduction actually has to do with molecular collisions. And you've probably heard about conduction before because metals are considered very good conductors. This is why you don't want to put metal forks in the electric socket when you get too bored while you're home. And it's also why pan handles get really hot if you have like metal or really cheap pans. Or if you leave a spoon in a hot pan, a metal spoon will often get really hot to the touch because that heat from the boiling water or cooking food in the pan is conducted through that matter and transferred in that way. Convection is the process of heat transfer by some mass movement or circulation in fluids. So convection, we've already talked a bit about convection when we talked about the Earth's mantle convecting and moving around. A really good example that you can look at in your house is boiling water on a stove. So convection, we're all really familiar with this process that water at the bottom of a pan gets hot. When it gets hot, it expands, and when it expands, it becomes less dense. Less dense things rise, and as they get to the top, they cool and then sink as they become more dense. So convection is largely based on temperature density differences and moving fluids away in that manner. And then the third type of heat transfer is radiation. And this is the process of heat transfer in all directions. So for example, we talk about, you know, the sun radiates energy in all directions. So kind of like when you draw your classic sun and you draw the waves going out in all directions, right? The lines all the way out from your little picture sun that you draw. That's kind of an example of trying to show what radiation looks like. So radiation, just know that heat can travel through space. Through radiation, it's radiated in all directions. And this is the process of how solar energy gets to Earth. Another example might be the heat radiating off of a campfire is an example of heat moving away from a source or heat transferring in all directions. So when we're thinking about solar energy, the sun actually emits three things. It emits light, heat, and ultraviolet rays. So heat is in the form of long wave radiation, and our UV rays are in the form of short wave radiation. Our light or visible light wave is kind of there in the middle. And so remember, there's lots of different types of electromagnetic radiation. And we have this thing when we're thinking about radiation called the electromagnetic spectrum. If you've taken physics anytime in your life, you've probably talked about this a little bit. So remember, we have really, really short wave gamma rays and X-rays. So these are really easily able to penetrate into the human body. That's why we use X-rays to look at, inside of our bodies. And then notice here on sort of the closest part of shortwave radiation to visible light, we have ultraviolet radiation. So our UV rays, the ones that cause sunburns and suntans and that type of thing, are here really close to the visible light spectrum. Here in the middle, sort of right between the short and long wave radiation distinction is visible light. So this is all of the light energy that we can see with our human eyes, right? And then violet, the darker colors are a little farther to the left on the electromagnetic spectrum. And then as we move towards the right, we go through the rainbow and get to red. And then in our long wave radiation, we have some microwaves and some radio waves. So as we move farther and further, these waves get wider and longer and longer. And then the shortest long wave, the long wave that's closest to visible light, is infrared light, which is actually you can think of it as heat. So for example, we use infrared technology to have night vision goggles so that we can use cameras, right? If you've ever watched like ghost hunting documentaries or shows where they have like infrared cameras to try and pick up heat spots, right? So think of that sort of as that radiation that we can't see with our human eyes, but we can sense. So again, the electromagnetic spectrum is based on wavelength. I don't want to go super in depth about it. If you're interested in it, we can chat more about it. But just know that the solar spectrum gives off 3 different wavelengths. It gives off UV light, visible light, and infrared light or heat. All right, so we have solar radiation coming to Earth. And 3 things can happen to it as it's incoming into the Earth's atmosphere and surface. So it can be absorbed. So it can be absorbed by objects and converted to heat. So my best example, or my favorite example, I guess, of solar radiation being absorbed by an object is think of, your kitty cat sunbathing in the window, right? Cats, we always say, are run on solar energy because they really like to bask in the sun. So, right, it feels really nice with the sun on your skin because you're absorbing that solar radiation. The second thing that can happen is that solar radiation can be transmitted. So it can be transferred by an object, but there is no heat created in that transfer. And the third thing that can happen is that it can be redirected. So it can bounce off objects through either reflection or scattering, right? So a good example of redirection of solar radiation would be the sun's energy or bouncing off of a window or glaring off of the top of a body of water. All right, so there's a couple of forms of redirection. We have reflection, which is when energy is bouncing off an object at the same angle and intensity as it came in, right? So down here in this diagram, we have A, reflection, where the energy comes in, it hits an object, and then it is reflected and bounced off at the same angle and intensity as it came in, right? So it's not scattered or anything as it hits that. So an example, think of reflection as your reflection in a mirror, right? There's you, and then in the mirror, you see something at the same angle and intensity, right? You don't have like some weird scattering happening to your image when you're looking in a mirror. The second type of redirection is scattering. If you move my head out of the way, you can see this picture better. But basically, you have solar radiation coming in, and what happens is the energy is dispersed in a lot of different directions, right? So the intensity is going to decrease so that the outgoing energy is less intense, but instead of going in one direction, it's going to go in a bunch of directions. An example of this might be like if we're going with reflection in A as you looking in a mirror, scattering might be an example. Think of some places where you can kind of see your reflection, but it's not super clear. So like maybe in like a window, you can sometimes kind of see your reflection, or in like a funhouse mirror where it distorts your reflection and scatters it around. Might be a good example of this process of scattering. All right, so solar radiation can be absorbed directly, it can be reflected, it can be scattered. And so when the sun's energy comes into the Earth system, what happens to that solar radiation is what we call the solar radiation balance, right? So it is in some balance. So for example, we have on this diagram solar radiation. So in our diagram, we have 100% of our solar radiation is coming into the system. And so about 50% of that 100% is absorbed by the land and sea. So it's directly absorbed by either the land surface or the ocean surface or other bodies of water. About 20% of that incoming radiation is absorbed by the atmosphere and clouds. About 20% is reflected from the clouds and bounces back out into space. About 5% is back scattered to space, right? So we lose, and about 5% is reflected off of the land or sea surface. So we have about 30% total of that original 100% is actually lost back to space through processes of reflection and scattering. So of our 100% incoming solar radiation, 50% is directly absorbed by the land and the ocean, 20% is directly absorbed by the atmosphere and clouds, and then about 30% is reflected back into space. This process of reflection or property of reflection is sometimes called albedo. So this word albedo means the fraction of radiation that is reflected back by a surface. So if we're talking about a specific object or surface, we can talk about the albedo of that surface. So for example, darker colored things tend to absorb more light and they aren't going to reflect much light back. While lighter colored objects typically reflect more radiation back. So this just has to do with the fact that different colors on the spectrum like to absorb or reflect more energy. So for example, think about if you're wearing a black t-shirt on a sunny day versus if you wear a white t-shirt on a sunny day and how different you feel. You typically feel hotter when you have black. You can even feel like how much heat your shirt is holding if you touch it. So when it finally gets warm outside this summer, do a little mini experiment where you wear a black versus a white shirt onto different sunny days and see how you feel. So that's just what this diagram is trying to show, that your dark roof, for example, is going to reflect less light than your light colored roof. Also, this is why asphalt gets very warm, because it is not reflecting very much energy. It's actually holding on and absorbing a lot of that solar energy.
So like when I was in marching band, we used to practice on the asphalt parking lot, and it would get so hot because asphalt basically just absorbs all the solar energy. And when we're thinking about albedo sort of naturally, so there's some examples of some human aspects here, but some important things to think about are that snow, so particularly our ice caps, are a really important system with high albedo. When we have more ice on Earth's surface, we are reflecting back more solar energy. And also, if we have thick clouds, think of white puffy clouds, they can also have a really high albedo. All right, so the greenhouse effect, let's now talk about the greenhouse effect, which has to do with the fact that radiation that is absorbed by the Earth's surface, right, so that 50% that is absorbed by the Earth's surface is eventually re-radiated as heat. So the Earth's surface absorbs radiation and re-radiates it as heat. And when that heat is radiated by the Earth's surface and oceans, there are gases in the atmosphere that can absorb that outgoing long wave radiation, particularly those gases that like to absorb that heat, right, that infrared wavelength heat that is radiated from the Earth's surface, are called greenhouse gases. And particularly important greenhouse gases on Earth are water vapor and carbon dioxide. So for example, this diagram showing you here in part 1 that we have shortwave solar radiation coming in and absorbing in the Earth's surface. And then the Earth's surface emits this long wave radiation, right? So our infrared radiation. And then the greenhouse gases in the atmosphere start to absorb it. So instead of that energy being able to escape into space, what happens is that it re-radiates some of that energy earthward, right? Trapping heat within the atmosphere. So the process of the greenhouse effect is just that radiation from the sun is absorbed by the Earth's surface, changed into heat. That heat is then trapped by gases in the atmosphere that can absorb it and re-radiate some of it back towards the Earth's surface. It's called the greenhouse effect because if you guys have ever been to a greenhouse, you know that a greenhouse is made of glass typically, so it's able to do the same thing. It allows the shortwave radiation from the sun to enter, but then long wave heat cannot travel through glass as easily, and so it's trapping that long wave radiation within it. That's why greenhouses are typically really humid and warm. The atmosphere does the same thing. Something that's important to mention about the greenhouse effect is actually if we didn't have the greenhouse effect on Earth, it would be too cold for lots of organisms that have evolved with the greenhouse effect to survive. So we would not be here if there was not a greenhouse effect. But the problem and why we talk about the greenhouse effect as a bad thing associated with climate change is that if there is too much greenhouse effect, then we have more warming than normal. So as I mentioned, the two main greenhouse gases are water vapor and carbon dioxide. And so carbon dioxide is a greenhouse gas. And so when we increase levels of carbon dioxide in the atmosphere, we get higher levels of that greenhouse effect. So when we have higher amounts of carbon dioxide in the atmosphere, we have higher levels of that heat absorption. We have higher levels of this heat radiation back towards the Earth's surface. So carbon dioxide is important in industry for a lot of reasons. And so that's because lots of the fossil fuels that we burn, coal, oil, and natural gas, are all formed from what we call hydrocarbons, so things that have carbon and hydrogen as the primary elements. And when we burn those carbon and hydrogens, we create or release carbon dioxide into the atmosphere through some chemical reactions. And so since the Industrial Revolution began, the use of fossil fuels has grown quite heavily. So now we really depend on all of those fossil fuels, coal, petroleum, and natural gas, but coal was the very first fossil fuel to be used at the very beginning of the Industrial Revolution. Think sort of at the beginning of America as a country. So as we're thinking about rising carbon dioxide levels in Earth's atmosphere, yes, fossil fuels are one of the primary reasons why we are seeing rising levels of carbon dioxide in the atmosphere today, and not just rising levels within natural variability, but sort of unprecedented rising levels that scientists have never seen through the rock record. And so, yes, fossil fuels are important to creating more carbon dioxide in the atmosphere, largely because our industry still relies quite heavily on fossil fuels. But also deforestation. When we are cutting and burning down trees, we also create carbon dioxide. And so deforestation is also one of the reasons why carbon dioxide levels are increasing. And there's actually some debate as to whether we should push back this rise in carbon dioxide later in time to when early agriculture appears, because we see some peaks from deforestation for really early agriculture thousands of years ago, which is pretty interesting. All right, guys, so go ahead and take a second, think about these questions, make sure you're able to answer them before we move on. So what is albedo? What is the greenhouse effect? And what is the primary source of increased carbon dioxide in the atmosphere today? All right, so you kind of just believe me when I say that scientists haven't seen this in the recent past, and it's sort of this unprecedented rise in carbon dioxide. And that's why people are so worried about climate change. It's not that it hasn't been hotter in the past. It was very, very hot during the Cretaceous when the dinosaurs were alive. And actually, because there was so much oxygen and it was so hot at that time, we get like these super big, super huge dinosaurs, super crazy big insects. I wouldn't want to be there. But it's just that the temperature is changing so quickly that we don't know what's going to happen to ecosystems and whether they can adapt that quickly. So that's why scientists are concerned about climate change. We don't know how it's going to change weather patterns. We don't know how it's going to change the way that animals associate with their environment, if they're going to be able to move to a better environment in time, because everything is happening so fast. So that's sort of the first disclaimer that I always want to say when we talk about climate change. And the other thing is that scientists do have some data about the past climate, and that data is based on lots of different things. It's based on using fossils and the animals that were alive. It's based a lot on isotope data, so using chemistry to understand what was happening in the past. And there's lots and lots of different ways that we can use. These are called climate proxies, to understand what was happening in the past. So scientists use lots and lots of different proxies from lots of different places and correlate those together to make a really robust reconstruction of what climate was like. But the one that people talk about the most, and kind of the record that started everything, is this Vostok ice core from Antarctica. So in the Antarctica Glacier, there is a place in Antarctica called Vostok, and the longest ice core in the world has been drilled from that place, Vostok, in Antarctica. And using the trapped gases within the glacier, scientists have looked at carbon dioxide concentrations over the last 400,000 years and created something that we call this sawtooth chart. Sorry guys, sawtooth chart, because it looks like if you have a saw, that the edges of what a saw looks like. And you know, I like nerd out about this stuff because I really like it and it's what I study. But I want you guys just to notice that there have been times in the past where we have had relatively high carbon dioxide. Those are what we call interglacial periods. So during these times, we didn't have a lot of glacial cover, and temperatures were fairly warm. And then there's also these periods through time where we have these really low carbon dioxide concentrations. These are related to ice ages. So periods when there was a lot of ice on Earth, temperatures were cold enough that we were able to get a lot of ice on Earth. So the most recent ice age was the one that they talk about in the Ice Age movie, the Pleistocene glaciation. And about 10,000 years ago, all those glaciers melted. And then we've seen this unprecedented change in temperature since then. Particularly in the last about 150 years, but really going back to the beginning of the Industrial Revolution. So you're like, that's cool that we have a carbon dioxide record from the Vostok ice core, but how do we infer or know that carbon dioxide is directly related to temperature? So one reason that we know that carbon dioxide levels are directly related to temperature is that we have modern observation, modern data to tell us that. But in the Vostok ice core, what's the really cool thing is that actually from the ice, we can get oxygen isotopes, and whether we have light or heavy isotopes can tell us about what the temperature was like. And so you can see that when we plot the carbon dioxide data, here we have some peaks in our carbon dioxide data, alongside the temperature data from the Vostok ice core, those curves match together really nicely. So that's evidence that as temperature increases, carbon dioxide is also increasing. So the relationship is actually, as we have more carbon dioxide in the atmosphere, atmospheric temperatures are increasing.